A whisper from the dawn of time still echoes through the cosmos. This is the story of the Primordial Echo, the first light of space, and it contains the universe's oldest secrets. By the end of this journey, you will understand how this ancient signal fundamentally reshapes our place in the cosmos. We will uncover why this faint glow is our most direct link to the Big Bang itself, and how its subtle imperfections contain the blueprint for all existence. What hidden truths about reality are locked within this cosmic fossil, and what does it reveal about the ultimate fate of everything? How does it feel to know we can perceive a message from the very beginning? This faint signal is the universe's baby picture, a photograph from a time before stars or galaxies even existed. We call this the cosmic microwave background radiation, but that technical name belies its profound nature. It is the afterglow of creation, the Big Bang's first and most enduring cry. To grasp its significance, think of the newborn cosmos not as empty space, but as an unimaginably hot, dense soup of energy and particles. For the first several 100,000 years, it was so thick that light was trapped, constantly bouncing around, unable to travel in a straight line. Then, in a pivotal moment, the expanding universe cooled just enough for atoms to form. Suddenly, the fog cleared. Light, which had been imprisoned, was set free in a brilliant flash. That first burst of light is what we detect today as the Primordial Echo. It has been stretching and cooling across the vastness of space for over 13 billion years, its energy fading from visible fire into the faint microwave hum we can now measure. This radiation is not coming from one direction, it permeates everything. It fills the room you are in right now. It is a cosmic fossil, a snapshot of the universe at the tender age of 380,000 years, capturing the precise moment the cosmos became transparent. When Nobel laureate George Smoot first saw the detailed map of this background, he described it as like seeing the face of God, because it offers a pristine, unedited look at the initial conditions of everything. This is not merely ancient light, it is our most direct line back to the origin, a constant whisper reminding us of our spectacularly violent and beautiful beginning. That persistent hiss was the sound of the universe itself. Two radio astronomers, Arno Penzias and Robert Wilson, were simply trying to do their jobs at Bell Labs in New Jersey. Their tool was a massive, sensitive horn antenna built for communication satellites, but they aimed it at the sky with a different purpose. Their goal was to map faint radio signals from our galaxy, but an infuriating, constant noise plagued their readings. It was a uniform static, a whisper coming from every direction, and it would not go away. They assumed it was a man-made problem or an equipment flaw. They painstakingly checked every connection. They even found a pair of pigeons nesting in the antenna, and convinced their droppings were the culprits, they carefully cleaned the entire apparatus. Yet the hiss remained unwavering and mysterious. They had no idea they were listening to the oldest song in existence. Meanwhile, just a short distance away at Princeton University, a team led by physicist Robert Dicke was actively building a detector to find this very signal. They had theorized that if the Big Bang were real, the entire universe should be filled with a faint, cool remnant glow. When the two groups connected, the realization was electric. Penzias and Wilson's annoying background noise was not a technical fault. It was the cosmic microwave background radiation, the cooled and stretched light from the universe's fiery birth. This was not a discovery born from a direct hunt. It was a glorious accident, a case of scientists stumbling upon the answer to the cosmos's greatest question while trying to solve a much smaller, earthly puzzle. For this serendipitous breakthrough, which confirmed a cornerstone of the Big Bang theory and effectively ended the scientific debate about the universe's origin, Penzias and Wilson received the Nobel Prize in Physics. Their story is a powerful reminder that the universe often reveals its deepest secrets to those who are simply persistent enough to ask, "What is that noise?" So what exactly are we looking at when we study this ancient echo? The cosmic microwave background is not the brilliant visible light we see from stars. It is a far colder, fainter remnant, a whisper in the form of microwave radiation. To understand this transformation, we need to journey back to that pivotal moment, an event cosmologists call the Epoch of Recombination. For hundreds of thousands of years after the Big Bang, the universe was an inferno of charged particles, a searing, opaque fog. Protons and electrons, all separate and free, buzzed in a dense plasma. Photons of light were trapped in this chaos, constantly bouncing off the free electrons, unable to travel any meaningful distance. The cosmos was a blinding, impenetrable glow. Then, as the universe continued to expand and cool, it reached a critical temperature. Suddenly, electrons could finally be captured by protons, combining to form the very first neutral hydrogen atoms. This was the moment the fog lifted. With most electrons now bound into atoms, the roads were cleared. The photons that had been trapped and scattered were suddenly set free, streaming across the universe in all directions. That first flash of liberation is the light we detect today. But over 13 billion years, the very fabric of space has stretched, and with it, that primordial light has been stretched too. Its waves have been pulled to incredible lengths, its energy fading from the heat of visible fire down to the cold whisper of microwaves. Yet this fossilized light is not perfectly smooth. Embedded within its uniform glow are the most precious clues of all: tiny fluctuations in temperature, variations of just a few millionths of a degree. These minuscule ripples are the seeds of everything we see today. They are the gravitational fingerprints of the first density variations in the cosmos, the places where matter ever so slightly began to clump together. From these tiny imperfections drawn by gravity would eventually grow the vast cosmic web of galaxies, stars, and planets. By meticulously mapping these faint patterns, cosmologists are not just looking at a baby picture, they are reading the universe's fundamental blueprint. This map reveals the precise ingredients of the cosmos, its exact age, and even hints at its ultimate destiny. But to truly read this blueprint, we needed more than a blurry snapshot. We needed a high-definition portrait of the infant universe, and that required going to space. Earth's atmosphere is a noisy, shimmering veil that distorts the faint whisper of the cosmic microwave background. So, scientists built and launched extraordinary observatories designed to listen from the silent vacuum beyond our planet. 2 missions, in particular, transformed our understanding. NASA Wilkinson Microwave Anisotropy Probe, known as WMAP, and the European Space Agency's Planck satellite. These were not simple cameras. They were technological marvels, ultra-sensitive instruments cooled to temperatures just a fraction of a degree above absolute zero, designed to map the entire sky and measure those incredibly subtle temperature variations in the ancient light. WMAP, launched in 2001, gave us our first finely detailed map. It was like putting on a pair of glasses for the first time and seeing the individual brushstrokes in a masterpiece we had only ever glimpsed from a distance. But Planck went even further. With its superior sensitivity, it refined those measurements, sharpening the image to an astonishing degree. it peered back to within a tiny fraction of a second after the Big Bang itself. The data these missions sent back was nothing short of revolutionary. They gave us the universe's vital statistics with breathtaking precision. We learned its exact age, 13.8 billion years. We confirmed its composition, a cosmic recipe that is both humbling and mysterious. Only about 5% is the ordinary matter, the stars, planets, and everything we see and are made of. 27% is dark matter, an invisible gravitational glue that holds galaxies together, and a staggering 68% is dark energy, the mysterious force driving the accelerated expansion of the cosmos. These missions also confirmed the universe's geometry is flat, meaning parallel lines never meet, and the laws of geometry we learned in school hold true on the grandest of scales. This quantitative data transformed the cosmic microwave background from a fascinating curiosity into the unshakable cornerstone of the standard model of cosmology. It provided a solid, measurable foundation for our entire cosmic history, a timeline we can now test and refine with incredible accuracy. Those faint ripples in the cosmic background are a message from a time before time, as we know it, had even begun. They tell a story that starts in the quantum realm, a world of inherent uncertainty and constant tiny jitters. In the very first fraction of a second, the universe is thought to have undergone an unimaginable growth spurt called cosmic inflation. It expanded faster than the speed of light, doubling in size repeatedly in an interval so brief it defies human comprehension. During this explosive moment, something miraculous happened. The microscopic quantum fluctuations, the random jitters that are a fundamental property of the vacuum of space itself, were caught in this expansion and stretched to an astronomical scale. Think of a tiny, microscopic wrinkle on the surface of a balloon. Now, imagine inflating that balloon to the size of the entire Earth. That minuscule wrinkle becomes a massive, continent-sized ridge. This is precisely what inflation did to the quantum jitters of the newborn cosmos. They were amplified into the slight differences in density, the gravitational seeds that are permanently etched into the cosmic microwave background. Without this process, the universe would be utterly different. There would be no clumps of matter, no gravitational gathering points. It would be a vast, smooth, and profoundly empty sea of uniform gas, a cosmos without stars, without planets, and without us. The specific pattern of hot and cold spots we see in that ancient light is a direct snapshot of those stretched quantum waves. It is our most powerful evidence for inflation, a fossil record from the first trillionth of a second. This means that the largest structures in the universe, the great walls of galaxies and the immense cosmic voids, owe their existence to the tiniest possible vibrations in the fabric of reality. The quantum whispers of the beginning became the gravitational roar that shaped everything. This ancient light also carries a sound, the deep, resonant tone of creation itself. Within the subtle temperature patterns of the cosmic microwave background, scientists found the fossilized imprint of sound waves that once rippled through the primordial fire. To understand this, picture the universe before it became transparent, that hot, dense plasma of particles and light. In that searing fluid, ordinary matter, which scientists call baryons, was tightly locked together with photons. They were not separate entities but a single, churning substance, a cosmic fluid, and in any fluid, pressure waves can travel. These were the universe's first sounds, vast acoustic oscillations pulsing through the newborn cosmos. They were not sounds we could hear, but colossal waves of compression and rarefaction, regions of slightly higher and lower density moving outward from every initial lump of matter at a significant fraction of the speed of light. Then came the moment of recombination, The universe cooled, atoms formed, and the photons suddenly streamed away. In that instant, the music stopped. The waves froze in place, their final positions permanently etched into the fabric of space. This created a very specific pattern in the cosmic background, a series of faint, concentric rings, like ripples from a stone dropped into a pond, but on a cosmic scale. The most important feature is the size of the largest possible ripple, a specific distance a sound wave could travel from the beginning until the moment the music ceased. This distance is known as the Baryon acoustic oscillation scale. It became a standard ruler stamped onto the cosmos. Incredibly, we can see this same ruler at work in the universe today. When we map the positions of millions of galaxies, we find they are slightly more likely to be separated by this exact same scale. It is as if the galaxies formed preferentially along the crests of those frozen sound waves. So this sonic fossil gives us two independent ways to measure the expansion of the universe. We see the imprint of the ruler in the ancient light, and then we see how that same ruler has been stretched by cosmic expansion in the modern galaxy maps. The two measurements agree perfectly, confirming our cosmic timeline with astonishing precision. The early universe rang like a bell, and the echo of that single, defining note still shapes everything we see. This ancient light serves as the universe's ultimate thermometer. Its temperature reads 2.725 Kelvin, a value just a few degrees above the coldest possible temperature, absolute zero. But the truly astonishing fact is not just how cold it is, but how perfectly it matches a fundamental physical ideal known as a blackbody spectrum. Imagine an object that absorbs every single bit of light and energy that falls upon it, and then re-emits that energy with a very specific and predictable signature. This is a blackbody, a theoretical concept that describes thermal radiation perfectly. The cosmic microwave background is the most perfect, the most precise blackbody spectrum ever measured in all of nature. Its curve of intensity across different wavelengths aligns with the theoretical prediction with almost unbelievable accuracy. This near perfection was definitively confirmed by a groundbreaking space mission called the Cosmic Background Explorer, or COBE. The data it sent back showed a plot so smooth and so perfect that scientists described it as the universe drawing a curve through its own data points. What does this incredible precision tell us? It reveals that the early universe was in a state of near-perfect thermal equilibrium. That hot, dense primordial soup was incredibly uniform and homogeneous, with energy being constantly absorbed and re-emitted in a smooth, balanced dance. This perfect blackbody spectrum is a powerful seal of approval for the standard Big Bang model. If there had been major disturbances later in cosmic history, enormous energy injections from unknown processes or collisions with other universes, they would have left scars distorting this perfect curve. The fact that we see no such distortions means the narrative of a hot, dense beginning followed by a smooth, quiet expansion is overwhelmingly correct. This makes the cosmic microwave background more than a picture or a sound recording. It is a pristine cosmic thermometer, confirming the thermal history of everything with unwavering and silent precision. Yet this pristine cosmic thermometer holds a few disturbing quirks. For all its breathtaking uniformity, the map of the cosmic microwave background is not perfect. It contains strange, large-scale anomalies that seem to defy one of cosmology's most cherished principles, the idea that the universe on the largest scales should look the same in every direction. This foundational concept, called the cosmological principle, is what allows us to assume our place in the cosmos is not special. But these anomalies suggest we might need to rethink that assumption. One of the most puzzling is a feature so strange that scientists gave it a dramatic nickname, the axis of evil. This is not a physical axis, but an unexpected alignment. Certain large-scale patterns in the cosmic microwave background, fluctuations that should be oriented randomly, appear to be subtly coordinated, lining up with the plane of our own solar system. It is as if the universe's oldest fossil somehow knows about our local cosmic neighborhood, a connection that should be impossible. Why would the echo of the Big Bang care about the orientation of our sun and planets? Other oddities deepen the mystery. There is a vast, unexplained cold spot in the sky, a region significantly cooler than the surrounding background, far larger than any standard fluctuation should allow. And there is a curious hemispheric asymmetry, where one half of the sky has a slightly different average temperature than the other half. The odds of these features arising from simple chance are incredibly low. So what could they be? Are they mere statistical flukes, ghosts in the data that will vanish with more precise measurements? Or are they cracks in the foundation of our current models, hints of physics we have not yet discovered? Some theorists propose radical ideas. Perhaps these alignments are a cosmic bruise, evidence of a collision with another universe in a vast multiverse. Maybe they are an imprint from a time before the Big Bang, a relic of a previous cosmic cycle, or perhaps the shape of space-time itself is more complex than we ever imagined, with a topology that twists back on itself. These anomalies are a humbling reminder. They tell us that the primordial echo is not just a confirmation of what we know, it is also a messenger pointing toward the profound secrets we have yet to unravel. That perfect cosmic thermometer holds an even deeper secret, a hidden signature of the invisible. The primordial echo is our most powerful tool for studying dark matter, the mysterious substance that makes up over a quarter of everything in the universe, yet refuses to interact with light in any way we can directly detect. We cannot see it, touch it, or trap it, but we can watch it shape the oldest light there is. The gravitational influence of dark matter was sculpting the cosmos from the very beginning, and its fingerprints are permanently etched into the patterns of the cosmic microwave background. Think of the early universe as a vast, shallow sea. The tiny ripples in the cosmic microwave background are like waves on the surface of that sea. But what determines the exact shape and size of those waves? It is the landscape of the seafloor itself, a landscape shaped by the gravitational pull of unseen masses lurking in the depths. Dark matter was that hidden seafloor. Because it does not interact with light or normal matter through any force except gravity, it was able to start clumping together long before ordinary atoms could. It formed an invisible gravitational scaffold, a cosmic skeleton. The subtle temperature fluctuations we see in the ancient light are not just random. Their statistical properties, the specific ways hotter and colder spots are distributed and correlated across the sky, are a precise record of how all matter, both visible and dark, was clustered in that infant universe. By analyzing this intricate pattern with immense precision, cosmologists can perform a kind of cosmic accounting. They can measure the total amount of matter present and then distinguish how much of it is the normal, atomic matter we are made of, and how much must be this mysterious, invisible dark matter. The patterns tell a clear and compelling story. Without the gravitational pull of dark matter providing deep, stable wells for normal matter to fall into, the universe would have struggled to form anything at all. The hot, fast-moving plasma of ordinary matter would have simply smoothed itself out, its radiation pressure blowing apart any fledgling structures before they could take hold. Dark matter's calm, relentless gravity provided the anchor, the seeds around which the first galaxies could eventually coalesce. If you were to remove dark matter from the equations, the statistical signature in the cosmic microwave background would be entirely different, a much weaker and less structured pattern incapable of building the grand universe we inhabit. So this ancient light does more than just prove dark matter exists. It measures its abundance with stunning accuracy, confirming that this invisible component is the dominant form of matter, the silent architect of our cosmic home. Yet the most profound secret locked within this ancient light is the signature of our own cosmic fate. Beyond confirming the existence of dark matter, the patterns in the cosmic microwave background reveal something even more startling: the presence of a dominant, repulsive force pushing the universe apart. This is dark energy. Its discovery was a true shock to the scientific community, and the Primordial Echo played a pivotal role in confirming it. The story begins with observations of distant stellar explosions, supernova, which showed that the expansion of the universe is not slowing down as everyone expected, but is instead accelerating. Something was actively pushing galaxies away from each other faster and faster. But how could we be sure this was real? The answer came from the blueprint of the early universe. The specific pattern of the frozen sound waves in the cosmic microwave background is exquisitely sensitive to the geometry of the cosmos. Think of it like this: the way echoes behave in a vast, empty hall is different from how they sound in a small, cluttered room. The geometry of the space defines the sound. The precise measurements from space telescopes confirmed that our universe is geometrically flat. This flatness tells us the total density of all the energy in the cosmos, a critical number. We already knew from the same day to how much of that density comes from ordinary matter and dark matter combined. When you add it all up, there is a huge piece missing. To have a flat universe, you need 100% of the critical density, but matter of all kinds only accounts for about 32%. The remaining 68% must be something else, a form of energy woven into the fabric of space itself. That missing component is dark energy, so the ancient whisper does more than tell us about the past. It carries an indelible stamp of the universe's future, a future of perpetual and accelerating expansion driven by this mysterious, dominant force. The first light illuminates not only our origin but our ultimate destiny. The story of this ancient light goes deeper than temperature alone. It also carries a hidden direction, a property known as polarization. This is the light's subtle way of remembering its very last interaction, a final push from an electron just before it was set free to travel across the cosmos. As the universe approached that moment of transparency, the dense plasma was a chaotic scene. Photons were constantly bouncing off free electrons in a process called Thomson scattering. But in that final instant, just as an electron was captured to form an atom, it gave one last directional shove to the photon escaping from it. That final interaction imprinted a specific orientation, or polarization, onto the light, a faint memory of its last collision now frozen in time for over 13 billion years. This polarization creates two distinct patterns in the sky, patterns cosmologists call E modes and B modes. Think of E modes as simple, radiating patterns, like the lines of force around a magnet or the gentle ripples from a stone dropped in a pond. These are generated by the ordinary density fluctuations, the same clumping of matter that created the temperature variations. They are the universe's straightforward signature. But the B modes are something else entirely. They are curling, twisting patterns like the swirl of water going down a drain. These are the true treasure, the signal that could change everything. They are thought to be generated by primordial gravitational waves, ripples in the very fabric of spacetime itself, created during the explosive period of cosmic inflation. Detecting these primordial B modes would be the ultimate smoking gun. It would be direct, tangible proof that inflation happened, and it would open a window to an almost impossibly early moment when the universe was just a trillionth of a trillionth of a trillionth of a second old. This would allow us to probe the energy scales at which all the fundamental forces of nature were once unified. The hunt for this signal is one of the most intense quests in modern science. Teams have built incredibly sensitive telescopes in some of the most remote and pristine places on Earth, from the high deserts of Chile to the South Pole, places where the dry, thin air offers the clearest possible view. There have been thrilling announcements of potential detections, followed by intense scrutiny and often disappointment as the signals were attributed to interstellar dust within our own galaxy. This search pushes our technology to its absolute limits, requiring instruments of astonishing precision and patience over many years. The elusive B-mode signal remains the holy grail, a whisper within a whisper that could validate our grandest theories about the very first moment of everything. The universe did not remain a tranquil sea of neutral gas for long. After its dark ages, a cosmic dawn was breaking. The first stars and galaxies ignited, and their fierce ultraviolet light began to flood the cosmos, tearing electrons away from the very atoms that had just formed. This was the Epoch of Re-ionization, a second great transformation that ended the darkness and lit up the universe for good. As this intense radiation swept through space, it re-ionized the vast clouds of neutral hydrogen, creating a new ocean of free electrons. And the ancient cosmic microwave background, still traveling across the universe, had to pass right through it. Most of the primordial photons sailed through undisturbed, but a small fraction of them, about 1 in 10, did something remarkable. They scattered. For a second time in cosmic history, these ancient particles of light were deflected by free electrons. This final, fleeting interaction left a ghostly signature on the light, a subtle but permanent scar. It imprinted a specific, large-scale pattern of polarization, a faint swirl across the sky that overlays the primordial signal. Think of it as a gentle fog that slightly blurs a perfect photograph. This secondary scattering also has a smearing effect, slightly smoothing out the smallest temperature variations in the cosmic background. Why does this matter? Because this ghostly imprint is our only direct window into that pivotal era. By meticulously measuring this large-scale polarization, cosmologists can work backwards. They can determine when reionization began, how long it lasted, and even infer the nature of the very first objects that caused it. Were the first stars monstrously large and brilliant, or did small, numerous galaxies do most of the work? The answers are encoded in this faint echo of a second scattering. This means the cosmic microwave background is not just a snapshot from 380,000 years after the Big Bang. It is a layered palimpsest, a document on which the entire history of the universe has left its mark, including the moment the first light switched on and forever changed the cosmos. This single, ancient photograph of our universe raises a question of staggering proportions. Why does it look exactly like this? The primordial echo reveals a cosmos that is not just habitable, but almost unnervingly perfect for the emergence of complexity and life. The initial conditions were balanced on a razor's edge. The strength of the primordial fluctuations, the rate of expansion, the density of matter, all of these fundamental numbers had to be calibrated with a precision that defies belief. Alter any one of them by even a minuscule amount, and the universe would be a barren void or a collapsed mess, utterly incapable of hosting galaxies, stars, or us. This incredible fine-tuning presents a profound puzzle. Is it simply a cosmic coincidence, a 1 in a trillion stroke of luck, or is there a deeper reason? For some of the world's leading physicists, the answer lies in a concept so vast it challenges the very definition of reality, the multiverse. In this radical view, our entire observable cosmos, with its hundreds of billions of galaxies, is not the entire story. It is just one bubble in an infinite, frothing sea of eternally inflating space, a meta-universe where new bubble universes are constantly budding into existence, each with its own unique set of physical laws and constants. Within this endless cosmic foam, every possible configuration of reality is realized somewhere. Most of these universes would be stillborn or sterile. But in a tiny fraction of them, the numbers would, by pure chance, line up just right for life to emerge. We do not live in a specially tuned universe. We simply live in one of the rare bubbles where the tuning allows us to be here to ponder it. This is known as the Anthropic Principle in its most expansive form. So what does this mean for the cosmic microwave background? Its specific patterns, the exact amplitude of its fluctuations, the size of its hot and cold spots, might not be fundamental laws of nature. They could simply be a local artifact, a random draw from an infinite cosmic lottery. Our universe's baby picture is not a portrait of all reality, but a single snapshot from a family album of infinite possibilities. While the multiverse remains a philosophical and mathematical construct beyond the reach of our current experiments, some researchers wonder if the ancient light has already given us a hint. Could the strange anomalies like the large cold spot or the unexpected alignments be more than just statistical ghosts? Perhaps they are cosmic bruises, the imprints of a long-ago collision with a neighboring bubble universe in the vast inflationary foam. Finding such a scar would be a revolution, the first tangible evidence that our cosmos is not alone. The search continues, probing the deepest mysteries of existence, all guided by the faint, cold whisper of the first light. This relentless pursuit of the universe's first sound is now accelerating. A new generation of cosmic listeners is emerging, instruments of such breathtaking sensitivity they will strain to hear the faintest murmurs within the ancient echo. On remote mountaintops in Chile's Atacama Desert and at the South Pole, colossal arrays of telescopes are taking shape under projects like the Simons Observatory and the even more ambitious CMB-S4. These are not single devices but vast fields of detectors, thousands of them, working in concert to scan the sky with a precision we have never before achieved. Their primary target remains the Holy Grail, the twisting B-mode polarization from primordial gravitational waves. But their mission is far broader. They will act as cosmic cartographers of the invisible, using a subtle effect called gravitational lensing. Just as a curved piece of glass distorts the view of a landscape, the gravitational pull of all the matter in the universe, both light and dark, subtly warps the path of the ancient light as it travels to us. By measuring these minute distortions in the cosmic microwave background's pattern, these next-generation observatories will create a map. This will not be a map of light, but a map of mass, a three-dimensional census of every galaxy cluster and every filament of dark matter stretching across the cosmos. They will quite literally chart the invisible skeleton of our universe. Meanwhile, proposed space missions like Lightbird are being designed to escape Earth's atmospheric noise entirely. From the quiet vantage point of space, its goal is to survey the entire sky, searching for any tiny, telltale imperfection in the cosmic microwave background's perfect blackbody spectrum. These spectral distortions would be the smoking gun for colossal energy injections in the universe's infancy, perhaps from the decay of exotic particles or the evaporation of primordial black holes. These machines are pushing the boundaries of what is measurable. They are not just telescopes, they are time machines probing realms of energy and instant so remote that our most powerful particle accelerators on Earth could never hope to reach them. The cosmos itself becomes our ultimate laboratory, and its oldest light is the key that unlocks the door. That faint, cold whisper from the dawn of time now presents us with a modern crisis. A single number, the Hubble constant, which measures how fast the universe is expanding today, has become the center of a fierce debate. We have two completely independent ways to measure it, and they stubbornly refuse to agree. The first method uses our most trusted cosmic fossil, the cosmic microwave background. By feeding its detailed pattern, the precise layout of those hot and cold spots, into our standard model of cosmology, we can run the cosmic film forward. The model calculates exactly how the universe should have evolved from that infant state to the present day, spitting out a predicted value for the current expansion rate. This method gives us one number. The second method is far more direct. We look at relatively nearby galaxies and measure their distances and speeds using brilliant stellar explosions and other well-understood celestial mile markers. This local measurement gives us a different number. The discrepancy is small, only a few percent, but it is real and it is persistent. It is not a simple error bar that can be dismissed. This is the Hubble tension. Think of it like two different clocks, one built from the universe's blueprint and the other built from observing its current motion. They are both precision instruments, yet they tick at undeniably different rates. This is not just a minor accounting error. It is a direct challenge to our most fundamental understanding of cosmic history. If our standard model is correct, these two numbers must agree. The fact that they do not mean something in our model is wrong, or at least incomplete. So what could be missing from the recipe? Perhaps our inventory of the cosmos is incomplete. Maybe there was an additional, unknown type of lightweight particle in the early universe, like a new form of neutrino, that subtly changed how radiation and matter interacted, altering the expansion history just enough to throw off the prediction. Or perhaps dark energy, the force driving cosmic acceleration, is not the constant, unchanging presence we assume it to be. What if its strength has been evolving over billions of years, subtly tweaking the expansion rate in a way our models do not account for? The most profound possibility is that we have misunderstood the physics of the primordial universe itself, the very physics encoded in that ancient light. The Hubble tension is more than a puzzle, it is a potential gateway. Resolving it is not about forcing the numbers to match. It is about listening to what the discrepancy is trying to tell us, a faint signal hidden within a conflict that may guide us to the next revolution in cosmology. The blueprint for our existence is written into the universe's oldest light with unnerving precision. Those tiny temperature fluctuations in the cosmic microwave background, the seeds for all future structure, had to be just right. If the gravitational fingerprints had been significantly weaker, the gentle tug of matter on matter would have been too feeble to ever overcome the universe's relentless expansion. Gas would have remained a thin, featureless haze, never condensing into the first stars or the great galactic cities we see today. The cosmos would be a dark and empty void without a single light to shine. On the other hand, if those initial ripples had been much stronger, the consequences would have been equally catastrophic. Matter would have clumped together with ferocious intensity, rapidly collapsing into a universe dominated by monstrous black holes. There would be no stable solar systems, no gentle stellar nurseries, only a violent and short-lived cosmic drama. Our universe seems to have found a perfect middle path, a narrow ledge between a barren emptiness and a chaotic inferno. This apparent fine-tuning leads to a profound and controversial idea known as the Anthropic Principle. In its simplest form, it suggests that the universe we observe must have the properties necessary for our existence because we are here to observe it. We are not accidental tourists in a random cosmos. Our very presence as conscious beings capable of measuring the cosmic microwave background is a direct consequence of the specific, life-allowing conditions that the background itself reveals. This is not a claim that the universe was designed for us, but rather a recognition of a stark selection effect. In a cosmos where the fundamental constants were even slightly different, there would be no one to wonder about them. We are a product of this particular cosmic configuration, a configuration whose successful recipe for complexity is permanently encoded in the first light. The fact that we can decode this message is in itself a part of the message. This ancient light is a cosmic dig site layered with the history of everything. Studying it is a form of high-stakes archaeology, where instead of brushing dust from pottery, we peel back layers of time. Each subtle statistical signature in the primordial echo corresponds to a different era, a different chapter in the universe's story. The most prominent layer, the map of hot and cold spots we call temperature anisotropies, is our primary artifact from the universe at the tender age of 380,000 years. It is the foundational stratum, the snapshot of the moment the cosmic fog cleared. But we do not stop there. By analyzing the specific polarization patterns known as E-modes, we can infer the dynamic motions of that primordial plasma. These are not just static lumps of matter. We can hear the sloshing of that hot fluid, the currents and flows that were present just as light was set free. This gives us a moving picture of the infant cosmos, not just a still photograph. The hunt for the elusive B-mode polarization is the quest for a much deeper, almost mythical layer. Finding its twisting, curling pattern would be like unearthing a fossil from the very first instant, a direct imprint of the gravitational waves generated during cosmic inflation. It would allow us to tunnel back through time, past the moment of the Big Bang's flash, to probe the trillionth of a second when the entire cosmic expansion was triggered. And then there are the later additions, the inscriptions left on this ancient document by events that happened billions of years after it was created. The large-scale polarization from re-ionization tells the story of the first stars and galaxies switching on. The subtle warping of the background's patterns through gravitational lensing creates a map of all the matter, light and dark, that the photons encountered on their 13 billion-year journey to us. Each of these signatures is a different tool in our cosmic toolkit. By combining them, we can cross-check our story, building a coherent and verified timeline from the first unimaginable instant all the way to the present day. We are not just looking at a single fossil, we are conducting a full-scale excavation of time itself. This ancient whisper forces us to confront a staggering truth about reality itself. For centuries, philosophers and scientists debated whether the cosmos was eternal and unchanging, a steady-state existence with no beginning and no end. The cosmic microwave background shattered that idea. It is the most powerful empirical evidence we have that our universe is not eternal. It had a definite, fiery beginning, a moment we call the Big Bang. This single observation draws a line in the sand for our knowledge. The primordial echo marks a boundary, a veil drawn across time. We can trace the history of the cosmos back to that brilliant flash of liberation, but beyond that wall of opaque plasma, our current laws of physics simply break down. The concepts of before and after lose their meaning when time and space as we understand them are thought to have begun in that very event. So what then came before the Big Bang? The question itself may be a category error, like asking what is north of the North Pole. Our tools for inquiry, forged in this universe, may be fundamentally unequipped to probe what lies on the other side of that veil. Yet this scientific boundary does not shut down wonder, it amplifies it. It grounds centuries of metaphysical speculation in hard, measurable data. We now know, with a certainty born of meticulous observation, that the cosmos as we know it has a history. It has a finite past, a story that began in a state of unimaginable heat and density, and has been unfolding for 13.8 billion years. This does not, in itself, prove a theological creation event. But it does firmly establish that our universe is a dynamic, evolving entity with a starting point. The existence of that starting point resonates far beyond astrophysics, touching the deepest questions of philosophy and our own place within this grand temporal tapestry. We are not living in a static, eternal arena, but within a narrative that had a first chapter, a chapter whose final, cooled words we are only now learning to read. This ancient whisper has not remained confined to scientific journals. It has echoed powerfully through our culture, becoming a symbol of our deepest cosmic curiosity. Carl Sagan's seminal novel and later film Contact hinges on a profound discovery, though not of the cosmic microwave background itself. The protagonist finds a message from a vastly advanced alien civilization, but she finds it hidden within the seemingly random, infinite digits of pi, a number fundamental to the geometry of our universe. The real-world parallel, the awe that captures the public imagination in the same way, is often directed at the CMB. It is our own universe's message, hidden not in a mathematical constant, but in a faint static, a signal from the very beginning. This idea resonates because it touches the same nerve, the hope that the cosmos is speaking to us, and that we are learning to listen. Turn on any major documentary about the universe, and you will almost certainly see it, the iconic, mottled map of the cosmic microwave background, splashed across the screen like a cosmic Jackson Pollock painting. It has become the universal visual shorthand for the Big Bang, a snapshot of creation itself. The names of the missions that brought us this image have entered the lexicon of every science enthusiast. We speak of COBE, WMAP, and Planck not as obscure acronyms but as explorers, the vessels that journeyed into the past and returned with a picture of our origins. This cultural penetration is remarkable when you consider what it represents. A faint microwave signal, a temperature of just a few degrees above absolute zero, has become a powerful icon. It connects the most complex equations of cosmology with a universal, human yearning, the simple, timeless question, where did we come from? The primordial echo is more than data. It is a story we tell ourselves about our place in the cosmos, a testament to our relentless drive to understand the light from which we came. The same technology that listens to the universe's first whisper now touches your daily life in surprising ways. That relentless drive to detect a signal colder and fainter than anything previously imagined has forced engineers to invent entirely new capabilities, and those breakthroughs have spun off into the world. To capture the cosmic microwave background, you need detectors of almost supernatural sensitivity. This pushed the science of cryogenics, the art of creating extreme cold, to its absolute limits. The entire focal plane of a telescope like the Planck satellite had to be cooled to just 1/10 of a degree above absolute zero. Achieving and maintaining such a profound chill for years in the harsh environment of space required radical new refrigeration techniques and super-insulating materials. These advances now help preserve biological samples, improve the performance of quantum computers, and enable more precise medical diagnostics. The signal from the early universe is also incredibly weak, buried under a mountain of terrestrial and galactic noise. To hear it, scientists had to pioneer a new generation of low-noise amplifiers. These are the ultimate signal boosters, capable of magnifying a faint whisper without adding their own distracting hiss. The very same amplifier technology born from this cosmic quest now forms the heart of the cellular networks that connect our phones. Every time you make a clear call from a remote location, you are benefiting from technology refined by the need to listen to the Big Bang. And then there is the data. a single CMB mapping experiment can produce petabytes of information, a chaotic flood of numbers that contains the subtle patterns of the ancient universe. Untangling this cosmic signal from the foreground clutter of our own galaxy required the invention of sophisticated new algorithms for pattern recognition and noise filtration. These powerful computational techniques designed to find order in cosmic chaos are now used to find subtle patterns in the human body. They enhance magnetic resonance imaging, or MRI, scans, allowing doctors to spot tumors earlier and with greater clarity. The same statistical methods that teased apart the universe's density fluctuations are now employed on Wall Street to model complex financial risks, and in tech companies to train the machine learning algorithms that power everything from speech recognition to product recommendations. Even the exquisite mirrors and precise calibration methods developed for these space telescopes have found their way into Earth observation satellites, improving weather forecasting and environmental monitoring. This is the hidden, practical legacy of our cosmic curiosity. The journey to understand our origins did not just give us a new story of creation. It gave us better tools for communication, for medicine, for understanding our own world. It is a powerful reminder that when we reach for the stars, we often find the technology to improve life right here at home. This ancient whisper does more than tell a story. It also acts as the universe's most fundamental clock and compass. It provides a fixed backdrop against which all motion can be measured, a cosmic reference frame that is the same for every possible observer. The most striking evidence for this is a subtle, large-scale pattern we call the dipole anisotropy. The cosmic microwave background is not perfectly uniform in every direction. One half of the sky appears very slightly warmer, while the opposite half appears just a fraction of a degree cooler. This is not a relic from the Big Bang. It is our own motion through space imprinted on the ancient light. Just as running through a gentle rain makes the drops seem to come at you from the front, our solar system's journey through the cosmos causes the primordial photons to appear blue-shifted and thus slightly warmer in the direction we are heading and redshifted or cooler behind us. By measuring this temperature difference, we can calculate our velocity relative to this fundamental rest frame. Our entire local group of galaxies is racing through the universe at an astonishing 370 kilometers per second, swept along by the gravitational pull of immense cosmic structures. This means we can measure our absolute speed through the cosmos, not relative to other galaxies, but relative to the very fabric of spacetime itself, as defined by the first light. Yet, when we subtract this effect of our own motion, the background reveals its true nature, an almost perfect uniformity in all other directions. This stunning sameness is the ultimate confirmation of the cosmological principle, the idea that the universe is homogeneous and isotropic on the largest scales. There are no special places, no center, and no edge. For any hypothetical civilization living in a distant galaxy, looking up at their sky with their own advanced instruments, the cosmic microwave background would appear almost identical. The same faint glow, the same pattern of microscopic ripples, the same universal clock reading 13.8 billion years. It is the one artifact, the one piece of data, that every conscious being in the cosmos could independently discover and agree upon. It is a shared inheritance from a time before stars, before planets, before any of the diverse structures that make each corner of the universe unique. In a cosmos of infinite variety, this ancient light is our common ground. This ancient whisper, for all its power, can only take us so far. It is a messenger from a specific moment, the universe's surface of last scattering, and it cannot speak directly of the times that came before. Think of it as a photograph of a newborn baby. You can see its features, its health, its potential, but the photograph does not show you the precise cellular divisions in the womb or the exact genetic instructions that were activated at conception. The cosmic microwave background is that baby picture for the cosmos. It gives us a pristine view of the universe at 380,000 years old, but the earlier, more violent chapters remain hidden behind a brilliant, opaque curtain. The entire inflationary epoch, that unimaginably fast expansion in the first fraction of a second, must be inferred from the subtle patterns it left behind, like deducing a storm from the arrangement of fallen leaves. And the very first instant, the so-called Planck era where the forces of nature were one, is a realm where our current laws of physics simply break down. The CMB points toward these mysteries but cannot directly illuminate them. Even the photograph we do have is not perfectly sharp. The ancient light has been subtly distorted on its 13 billion-year journey to us. The gravitational pull of all the matter it passed, the dark matter halos and the galaxy clusters, has acted like a vast cosmic lens, slightly warping and blurring the image. This effect, called gravitational lensing, means we are not seeing the primordial universe with perfect clarity. We are seeing it through the warped glass of its own later history. The picture is statistically perfect, revealing the overall distribution of those initial seeds, but it cannot show us the individual quantum events that created them. We see the forest, but not the individual trees shaking in that first quantum wind. This echo tells us the what and the when with breathtaking accuracy. We know the universe's age, its composition, and its geometry, but the ultimate why remains stubbornly beyond its reach. Why do these specific laws of physics exist? Why did inflation occur? Why did the quantum fluctuations have exactly the strength they did to allow for galaxies and life? The CMB frames these profound questions in stark relief, giving us the data to ask them with precision. But the answers lie in a shadowy realm that this first light, by its very nature, can never directly reveal. Buried within that ancient light's polarization is a hunt for another ghost, a signature of the universe's first magnetic fields. We are surrounded by magnetism, from the humble compass to the vast fields that weave through galaxies, but their ultimate origin remains one of cosmology's great puzzles. Did these fields only arise later, forged in the turbulent hearts of stars and supernova, or were they present at the very beginning? Scientists are now scouring the cosmic microwave background for clues, searching for the imprint of what are called primordial magnetic fields. The idea is that if such fields were generated in the universe's first moments, perhaps during the violent upheaval of inflation, or a dramatic phase transition when the fundamental forces split apart, they would have been woven into the fabric of spacetime itself. These primordial fields, even if incredibly weak, would have interacted with the hot, charged plasma of the early universe. As the primordial light made its final scatter off electrons, the presence of this all-pervading magnetism would have given the photons a subtle, characteristic twist. It would have imprinted a unique, curling pattern on the light's polarization, a specific kind of signature that is distinct from the one left by gravitational waves. Finding this faint spiral in the sky would be like discovering the fossilized root system of a giant tree, revealing that the magnetic fields we see today in galaxies have a deep cosmic origin, stretching all the way back to the Big Bang. The challenge is monumental. This signal is predicted to be exquisitely faint, drowned out by the polarization from density waves and the confounding swirls of interstellar dust within our own Milky Way. Disentangling this whisper from the cosmic static requires not just incredibly sensitive telescopes, but also a deep understanding of every other possible source of polarization across the sky. Yet the potential reward is worth the decades of effort. A confirmed detection would do more than just explain the ubiquity of magnetism. It would throw open a window to an era we can never recreate, a time when the universe was less than a second old, revealing the turbulent physics that shaped our reality long before the first star ever flickered into life. This faint glow from our past does more than illuminate our origins. It sketches our ultimate destiny. The same precise measurements of the cosmic microwave background that tell us the universe's age and composition also allow us to run the cosmic film forward, projecting the final chapter of everything. The prevailing model of cosmology, known as lambda CDM, is built directly upon the foundation laid by this ancient light. Its name comes from its two primary components, lambda representing the cosmological constant of dark energy, and CDM standing for cold dark matter. This model, calibrated to the exquisitely detailed patterns in the CMB, points toward a future that is both grand and profoundly lonely. It tells us that the expansion of the universe is not just continuing, it is accelerating, driven by the relentless push of dark energy. This acceleration is not a temporary phase, it is the defining feature of our cosmic fate. Imagine two leaves floating on the surface of a river that is steadily widening into an ocean. At first, they are close enough to influence one another, but as the expanse of water grows between them, they drift apart, carried by the current. Now, stretch this image to a cosmic scale. Billions of years from now, the expansion of space itself will have carried all other galaxies so far away from our own Milky Way that they will have vanished over the cosmic horizon. The light from those galaxies, no matter how powerful our telescopes, will no longer be able to reach us. Our island universe will be truly alone, adrift in a vast black emptiness. This is the first step toward a scenario cosmologists call the heat death, or the big freeze. As eons turn to ages, the last stars will slowly consume their nuclear fuel and flicker out. One by one, the lights of the universe will go dark. The cosmos, once a brilliant firework of creation, will become a cosmic graveyard, populated by the cold, dead remnants of stars, black holes, and drifting planets. And in the almost unimaginable depths of time that follow, even the fabric of matter itself may not be stable. Protons, the fundamental building blocks of atoms, are predicted to decay, dissolving the last coherent structures into a thin, uniform sea of radiation and elementary particles. The temperature of the entire universe will approach absolute zero, a state of maximum entropy where no energy can be extracted, no work can be done, and no new structure can ever form again. The universe will be cold, dark, and empty. It is a deeply poetic and somber symmetry. The cosmic microwave background is the cooled remnant of a hot, dense beginning, a fireball of immense energy. And the data it carries points toward a final state that is its exact opposite, a cold, dilute, and silent end. This ancient echo is not just a message from our birth, it is a whisper from our funeral, bookending the entire story of cosmic history from a fiery genesis to an icy, eternal stillness. This faint cosmic static is our most tangible link between two seemingly separate worlds. The cosmic microwave background elegantly bridges the vast domain of general relativity with the bizarre realm of quantum mechanics. General relativity masterfully describes the universe on its grandest stage, governing the gravity of galaxies and the expansion of space itself. Quantum mechanics, in stark contrast, rules the subatomic arena, a place of probability and uncertainty where particles flicker in and out of existence. For decades, these two theories have existed in separate boxes, one explaining the infinitely large, the other the infinitely small, with stubborn incompatibility. Yet the primordial echo unites them, those initial ripples in the cosmic background, the very seeds of galaxies, are believed to be quantum fluctuations born in the universe's first fleeting moments. During the explosive inflation period, these subatomic jitters were caught and stretched, magnified from the quantum scale to a cosmic one. The great walls of galaxies and the immense cosmic voids we map today are not random structures. They are, at their fundamental core, amplified quantum mechanical events. When cosmologists analyze the detailed statistics of the hot and cold spots in the ancient light, they are not just studying astronomy. They are, in a very real sense, conducting an experiment in quantum mechanics on a cosmological scale. This is quantum physics writ large across the sky, evidence that the probabilistic rules governing particles are inextricably woven into the fate of the entire cosmos. No laboratory on Earth could ever hope to demonstrate this connection, but the universe itself has provided the experiment, and its results are permanently etched into the first light. That full sky map of the ancient light is more than data, it is a work of art. The iconic oval, splashed with red and blue patches representing the faintest of temperature differences, has been called the universe's fingerprint. Its pattern is both chaotic and deeply ordered, a kind of abstract masterpiece painted by the laws of physics themselves. There is a profound mathematical elegance to its statistical simplicity, a symmetrical balance in the way the hot and cold spots are distributed that speaks to a fundamental harmony in the cosmos. It feels almost miraculous that the staggering complexity of our present universe, with its billions of galaxies and swirling nebulae, could have arisen from such a seemingly straightforward and minimalist blueprint. This inherent beauty is not a happy accident or a superficial side effect. For the theoretical physicists who spend their lives decoding reality, aesthetic appeal is often a guiding compass. When faced with multiple mathematical descriptions of the universe, they are frequently drawn to the one that possesses a certain elegance and simplicity, a quality that the cosmic microwave background radiates. The fact that this ancient echo is not just true but also beautiful stands as a powerful testament to a deep and enduring idea that the universe's most fundamental truths are often expressed in a language of profound and silent